of thermodynamics. Our sixth equation is called continuity. Now, this is a fancy word for something that's not really all that complex. It involves how patterns of convergence and divergence at the surface or aloft give rise to vertical motion. So, for example, as we're just seeing this slide, you can see how low-level convergence gives rise to rising motion and ultimately upper-level divergence. This overall process is called continuity. Sometimes you hear the term tube of toothpaste theorem. You squeeze the atmosphere from the sides and it goes up through the top. The final of the 7 primitive equations is conservation of water substance. And that's just a complex way of saying that we're talking about condensation and evaporation. We're talking about cloud droplet growths, things like the Bergeron process and collision and coalescence. We're talking about moisture advection. Any process that changes the amount of moisture in the air fits under this basic idea. The basic idea here is that you can't have condensation from air that has no humidity, things like that. Again, we learned all those kind of ideas in the second unit of the course. So to review the 7 primitive equations, you're going to think, hey, we've learned all this in this class, and that's exactly right. In fact, hidden in the idea behind ATS 113 is the idea that what you're really learning is about the basics of how the atmosphere works, just like a model learns what the basics of how the atmosphere works are. 3 of the basic things you have to know are about how the forces in the atmosphere give rise to motion. Another is the ideal gas law, the first law of thermodynamics, continuity, and the conservation of water substance. Taken together, these 7 equations, which are very complex equations that take enormous computer programs to compute them, but summarize the ideas that we learned at ATS 113, are really all that an atmospheric model or a weather model needs in order to make a forecast. So now that we have these 7 primitive equations, we need to ask ourselves, what are the computer models going to do with them in order to forecast the weather? Well, what do you do with any equation? You put numbers into it. And the numbers that we put into the 7 primitive equations are observations, like these that are taken in a Stevenson shelter at a National Weather Service office. This is the kind of specialized shelter in which we observe things like temperature, dew point, pressure, etc. So we take these observations all around the country and we put them onto a map. And the computer then takes these observations that are scattered at various sites around the country and it transforms them into a regular grid. Kind of like graph paper or kind of like a spreadsheet, there's now at every spot on the earth, on this grid, there's a temperature, there's a pressure, there are winds, there's humidity, etc. And the model knows where all these temperatures and pressures and such are. It then, at every one of those locations, will apply the 7 primitive equations. And the 7 primitive equations are prognostic. They predict how the temperature, pressure, winds, humidity, etc. are going to change. And so you apply the equations at all these points on this map, and you end up with a forecast for about 1 second later. The 7 primitive equations are prognostic, but they only make forecasts for very small time steps. This is an important vocabulary word, time steps. Very small intervals of time that the equations can make a forecast for. But after you've applied the equations to all those points and you have a new forecast of the temperature, pressure, humidity, winds, etc. at every grid point, you then apply the 7 primitive equations again. And now you have a forecast for 2 time steps, or about 2 seconds into the future. To make a 12-hour forecast, you're going to have to do this over 40,000 times. Good thing computers are fast and don't mind doing repetitive work. So every model has grid points, locations where it is making its forecast. This map here happens to show the locations of the grid points of a model called ADA. The name of the model is not important, but this is a very important model in the United States. It is run by the government, run by NOAA, the National Oceanographic and Atmospheric Administration, and you can see that these grid points are very close together. The ADA model can make detailed forecasts because it is a very high resolution model. We say that it's high resolution because the grid points are close together. On the other hand, if we look at the same grid points and we back out a little bit, we can see that there's a problem with the ADA model. It's a regional model. The grid points are very close together, but they only cover a small area of North America. Let's say that there's a cyclone out in the Central Pacific. Does the ADA model even know it's out there? No. Well, what if it turns out that that's important for what's going on in the U.S. weather? In that case, the ADA model will just be wrong. So it seems like what you would really want is not so much a regional model, but a global model, like this one, where there's grid points at every location on the globe. This happens to be a model called the MRF. Again, the name isn't important, but you can see that there is no area of the world that doesn't have a grid point in the MRF. But if you take a closer look, you can see that there's a problem with this. The resolution of the MRF and other global models isn't really all that good. There's only 2 grid points in the entire state of Nebraska. A lot of weather could be happening between those 2 grid points, and the MRF model wouldn't even know it's out there. And so there's between resolution and domain of a model. You could either have a model that has lots and lots of grid points very close to each other. It can have a very high resolution, but then it has to be regional. It can only cover a small area of the world. There aren't any computers out there fast enough to run a high resolution model for the entire world. If you want a forecast for the entire world, or you want your model to know about all the weather and all the major weather features of the world, then it has to be low resolution. It's always a trade-off. Okay, so the forecast models run. They're run on the biggest computers in the world. They run for a few hours to make a forecast for the next few days. Then it's important to disseminate the forecast. The forecast needs to get out that these models made to the forecasters. And there are a number of mechanisms by which this is done. In this picture, you can see that a guy is actually looking at maps that are pinned up to a wall. These maps were sent to him by a fax system. This is actually still quite common. You can go up to the 5th floor of the Hickson Lead building and see that we have a wall like this where every day faxes come in that bring in the forecast models. It's also very common now for these forecasts to be transmitted via the internet, whether from a website that is run by this one, for example, which is run by the National Weather Service, or by individual private companies, such as this, which is run by Unisys Weather. But if you go, and anyone can go to these websites. If you want to go to Unisys Weather and look up what the models are saying, you can do that. And if you go there, you're going to find out that there are a lot of forecast models. A number of different agencies in the United States and internationally have their own computer models. And all of the models are a little bit different. They have slightly different resolutions, slightly different domain. They make slightly different assumptions about how to solve the 7 primitive equations. How do we know which ones to look at? Well, we consult a crystal ball. And if the crystal ball is not available, we get our palms read by a gypsy. And failing that, consult Ronaldo the Great, who checks our tarot cards. Or we take a more scientific approach and do what's known as ensemble modeling. When we work with an ensemble of models, we are working with a collection of models. No individual model or computer program is ever completely right about the weather. And while some models are somewhat better than others, they all sometimes are right. So we look at a collection of results or an ensemble of results from several models, such as this diagram, which shows the position of a contour line on about 15 different models, and compare them, and we try to figure out what the consensus forecast is. The models are all saying something slightly different, but overall, what are the models saying? This is slightly different from an average. Consensus means we're trying to find a forecast that matches what most of the models are saying. And so it's the TV meteorologist's job, or the private meteorologist or whatever, to make sense of these models, to go through them, to look at his ensemble of models and decide what they mean for the weather today. To produce a forecast, then, that the public can consume, that it contains interpretation about things like fronts and cloud cover and rain, and this information to increase the safety and to increase the principally about safety and also about convenience of their audience. Now here's something the guys on TV wouldn't want you to know. The TV meteorologist's hard